The first session in POPL, and we will start with the paper implementation and synthesis of math library functions, and this will be presented by Pavel Panchekha.
All right, thank you, Sam. Is the audio working? Yes. All right, excellent. So actually, the intention was for my student in Briggs to give this talk, but then he went and graduated and is now verifying hardware for Amazon. So it feels like I'm in grad school again, very exciting to kick off POPL'. So this talk is about what happens when your program evaluates an elementary function, like sine or cosine, x or log. Because the thing is, you and I both know, there's no magic smoke inside these function implementations. They're using the same kind of primitive arithmetic operations that any other numeric code in your program uses. And this task of implementing elementary functions using primitive arithmetic, that's something that humanity's been working on for literally over 100 years. So that's kind of interesting. Why is it so hard? Like, why haven't we licked this problem yet? Most other problems in computing are not this old. Well, there's a lot of reasons. But I think one of them is relevant to this talk, is this idea of a speed-accuracy trade-off. See, what my students and I have shown in previous work is that if you accept slightly less accurate implementations of sine and cosine, well, there are trade-offs inside those implementations. There are choices you can make. And if you're okay with them being slightly less accurate, they can be quite a bit faster. In fact, depending on what accuracy you're willing to accept, you can see speed-ups of like 2, 3, 4, 5x. And that makes a real-world difference, especially in numerically intensive programs, like in physics, engineering, high-performance computing, and graphics or AI, that kind of thing. So if these really big speed-ups are available, as long as your application's willing to tolerate slightly lower accuracy, it really seems like what we should be doing is implementing application-specific versions of these math function implementations, ones that are perfectly suited to the accuracy and the performance requirements of whatever application you're doing. Maybe even not application-specific, maybe call site-specific. Maybe specific to every individual use case of your program. So that'd be cool. We could get big speed-ups. And again, in prior work, we've shown that this really does happen. You can do this thing. But mostly people don't. This kind of thing is pretty rare. So we asked ourselves, like, why is it rare? Why don't people write application-specific implementations of sine and cosine more often? And yes, okay, so one obvious answer is that there's some background you need. In that 150 years, we figured some stuff out. It might be relevant to your work. Fine. But I think actually the background issue isn't as big of a problem as you might think. First, you can learn it. Second, not all of it is relevant. You can do a pretty good job even without most of it. Honestly, having done some of this kind of work, I can tell you what the biggest reason not to write your own sine or cosine function is because of how many damn typos there are in the process of writing it. It is so easy to write a minus sign instead of a plus sign, and there goes your whole day. Because you have to find that mistake, or worse, you're going to do some kind of optimization work on the assumption you're getting good data, and then your data's total nonsense, of course, because you wrote a minus sign instead of a plus sign. And it's not just that. You can parenthesize things wrong. You can copy and paste some coefficient and lose a couple of digits at the end. You can forget to scale something. This is super common. Just as like a quick personal story here, I wrote the quadratic formula function in the Racket standard library. And supposedly, like, I'm supposed to be good at this kind of thing. And I was quite proud of this implementation. I spent a while on it. I came up with some novel algorithmic approaches that I was very happy with. I put in quite rigorous testing. I wrote a little paper proof of my work. I thought it was good stuff. So we shipped it in Racket, I think 8.6 or 8.7, and all was good. And then 2 years later, I get a bug report. And this bug report has this super carefully crafted quadratic formula. It's just this one formula they could find that it produces the wrong answer. So I was devastated. I was so happy with this work, and here there's a flaw. I look into it, and this is the bug fix. All I had forgotten to do is I had forgotten to rescale some kind of residual parameter. This code matters only for the rarest of inputs. This is an error handling variable in an error handling branch. It's crazy that this guy was even able to find this bug. So okay, that's a funny bug. It's a little embarrassing for me personally. If this is the problem I ship to production, think of how many versions of this I typed into my text editor and then had to debug. How many versions of this threw off earlier attempts at testing or threw off some optimization work I was doing. So that's what this talk is about. This talk is entirely about typos, and specifically it's about this DSL that my students and I have built, MegaLibm, to catch those typos before they throw off your work. MegaLibm is a workbench for writing these application-specific elementary function implementations. It's safe, it's modular, it's tunable, and I'm going to tell you a little bit about it. So let's start kind of at the core of one of these elementary function implementations, which is answering this question. We want to implement some kind of elementary function, but we don't have access to any cool elementary functions. What we've got are like plus, minus, times. If you're feeling spicy, you got division and square root. Which means that you only really have access to some small family of functions. If you've got plus, minus, and times, that's polynomials. If you add division, maybe you have rational functions. So at the core of any of these implementations, there's some kind of approximation of the elementary function you want by this restricted family of functions. And this is in real-world implementation. So for example, here's the AMD optimized compute libraries libm implementation of cosine. And what do we have in blue right here? It's a polynomial evaluation. It's a macro that expands to some code that evaluates a polynomial. And of course, if you can do this in C, you can do this same kind of very common operation in our DSL called MegaLibm. There's a construct called polynomial. You give it a list of coefficients. It evaluates a polynomial. But the superficial similarity of these two expressions belies a key difference at the type level. See, in C, the type of this expression is double. And what that means is that to the C compiler, any double precision value is exactly as good as any other. If you add a minus sign, that's still good. If you delete some terms in your coefficient, that's still fine. You can even, rearrange some stuff. C can't catch those mistakes. In MegaLibm, however, we're going to try to track the mathematical computation you're doing at the type level. So this term has a type. It says it's an implementation of a mathematical function. And the specific mathematical function for polynomial is that polynomial that you wrote down. Now, we're not trying to implement a polynomial. We're actually trying to implement cosine of x. And so we can express that intent to MegaLibm using the approx construct. So what approx does is it has a first argument telling you what function you're approximating, a last argument telling you how to do it, and it returns an implementation of cosine of x, its first argument, instead of an implementation of that polynomial. So basically, it's like a kind of cast. But a key thing this gives us is the ability to make the cast safe, because there's this middle argument, this epsilon, and that's an error bound on the difference, on the approximation error between cosine of x and that polynomial. And we can check this error bound at compile time. In fact, we can check it as part of the type system. Let me just show you how that works formally speaking. Let's write down a type rule for approx. This approx returns an implementation of its first argument. Here it returns an implementation of cosine of x. And it does that no matter what its last argument, the actual implementation, is computing. So here we have an implementation of a polynomial, and we cast it to an implementation of cosine. And this kind of cast is safe insofar as the difference between the two functions is bounded by epsilon. And so all of MegaLibm's type rules, they have these what we call semantic wellformedness conditions. These are mathematical properties, property of pure real numbers, that ensures that the steps you're taking in your implementation are reasonable. And we can check these automatically by dispatching to any number of mathematical tools. So like, it could be Mathematica or MATLAB, or there's loads of these kinds of solvers. Okay, so this is kind of our general approach to keeping things safe. Now let me zoom out a little bit, tell you how we can put these individual safe components together. Here's a more full graph of cosine of x. And if you look at it, one key property of cosine of x is that it's wiggly. And for mathematical reasons that honestly are a little beyond me, wiggly functions are hard to approximate with polynomials. Don't quote me on that theorem, but wiggly, bad. Luckily, there's a trick. We don't have to approximate this whole wiggly function using polynomials, because if you look carefully, this whole function is actually a copy and paste of that blue square right there, just with some flips and shifts added in. And that gives us an implementation technique called range reduction and reconstruction. The idea is, suppose we want to evaluate cosine of x on this point right here. It's outside that blue region. But what we can do is map it to the corresponding point in that blue region. That's called a reduced input. Then we can evaluate cosine within that blue region using, for example, a polynomial approximation, and that gives us what's called a reduced output. And then we can reconstruct the reduced output, and that gives us the final output for the original input. So this is a super common technique. That's how you do it in C. And you can do the same kind of thing in MegaLibm. There's a construct called right, and it's called right because you extend the valid range of inputs to the right. And this term, it takes E, which is the actual implementation to use in that blue region, as well as a reduction and a reconstruction function. And of course, just like any construct in MegaLibm, this one is safe. So here the type rule says that this is an implementation of f of x if it wraps an implementation of f of x, and moreover, if that reduction, application, and reconstruction is equivalent to the original. So there's the standard wellformedness side condition. But the really interesting thing happens when you nest these range reduction and reconstruction operators together. So here I've used right to extend the original blue region into like half a period of cosine, but I can send it to the left as well, and that gives me a full period of cosine. And then I can use this operator called periodic to actually extend it to the full range of floating point inputs. And of course, throughout the process, MegaLibm will track that range of applicable input variables to make sure that I don't make any mistakes. So that's how our core language, it provides this safety and this modularity. It makes sure you don't make mistakes, and you can build these things step by step. Now let me tell you a little bit about how we actually turn that into usable C implementations. Basically, we compile this code to C. So that's the full story. But there's some decisions you have to make. Even for something as simple as polynomial, there's more than one way that you could potentially implement a polynomial in C. There's Horner's rule, there's a Strins rule, there's all sorts of variations on these. And these decisions, even though they seem kind of trivial, they matter a lot. Horner rule on the left-hand side, for example, that's typically the most accurate way to evaluate a polynomial. But it's not the fastest. This middle rule, a Strins form, that works really well on vector hardware because you can combine some of these operations together. And this last one, that lets you can kind of split the difference between them. You can do a little bit of Horner's rule, a little bit of a Strins rule, mix them in various ways, and try to get the best of both. So if you want to get good performance and accuracy, you do have to mix. You do have to specify how exactly you're planning to do this. And in MegaLibm, you can do this by basically adding annotations to your expressions. These annotations modify the compiled code. They don't modify the type system or the semantics in the real numbers. So here, for example, I can take this polynomial rule, and I can specify a bunch of things about it. I can say do it in 64-bit, use a Strins form, split out some terms, do those terms in a different precision, and all sorts of other things. And other terms in MegaLibm, they have the same kind of properties. We can add new algorithms at the compile time stage using a technique like this. Of course, you'd have to be crazy smart to write this thing from scratch. I don't know anyone who could do it. But our idea in MegaLibm is that you can do this interactively. You can try something, see how that affects speed and accuracy, try something else, and repeat. And in order to support this workflow, MegaLibm is actually embedded inside Jupyter. So you can try something, you can write a little MegaLibm program, and then you can graph it, you can compare two different versions. So here, for example, you can tell that V2 on the right-hand side is slightly more accurate than V1 because the blue dots are lower. And then once you're happy with the results, you can export that to C. So that's kind of the idea of how people can use MegaLibm. And of course, we've used it a bunch. We've managed to replicate a bunch of existing implementations in popular math libraries. And we've typically managed to achieve comparable speed and accuracy to those original implementations. But of course, since we're implementing these in MegaLibm, they're shorter, they're safer, and they're probably a little bit easier to reuse or reuse chunks of. And it's kind of a little funny. In the process of doing this, we've actually found some bugs, exactly the same kind of bugs that I would make if I were doing this work. So not saying anything wrong about the authors. So like here, for example, this is a little snippet of a library called VDT, the cosine implementation. And if you've been heads down in the C standard, you'll probably immediately recognize that these first two terms are going to be parenthesized by the associativity rule. But that's actually not what you want to do. And MegaLibm, in this case, generates sort of automatically, it generates the more reasonable code, which parenthesizes the last two expressions, and that produces this much more accurate output. So we actually found some of these bugs in the process of this work. And moreover, because MegaLibm is kind of this interactive workbench, we're able to take some of those existing library implementations and just change some stuff. There's some tooling built into MegaLibm to like synthesize new polynomials or try out different ways of doing it. And we were able to get faster and more accurate variations on those original functions as part of this MegaLibm code. In this last column, you can see that the number of lines changed here is minuscule. We like change 1 or 2 lines of code. That means add 1 or 2 of these annotations, and things work better. So that's MegaLibm. It's our safe, modular, and tunable DSL for writing these math libraries. It uses some of the techniques that I've covered throughout this talk. And I'm happy to take any questions that you have.
Hello, can you hear me? Yep.
Yeah.
Thanks
Hello.
for the talk. My name is Arthur Charguero from INRIA. My question is about verification.
Yeah.
What are the plans? What can be done? In particular, can you use a GAPA tool to get some bounds on the errors that you are computing with the various versions that you generate?
That's a great question. So it seems natural to integrate verification into this. We played a little bit with tying this to FP Taylor, which is a tool you're probably familiar with. And that worked OK. Basically, from each of these like constructs in the DSL, we can generate an FP Taylor condition and have it verified. So I think that code bit rotted, but like it could be resurrected. I'm a little less familiar with GAPA, but I'm sure we could do something similar. And I think it would be very attractive, right, to generate verification conditions for these implementations. So yeah, great question. I'd love to do it. It's just my student graduated. And you know that once you become a professor, you lose the ability to program, except via email. So I'm a little stuck right now for how I might do that work.
Time to hire a new student.
I'm doing my best.
Hi, thanks for the great talk. I'm curious, in the rule for approx, you showed how the epsilon sort of was used in verifying that the approx was OK. But it didn't look like epsilon was tracked in the output type. So I'm wondering how those approximations work under composition. Can you use them again in another approx? How do the error bounds propagate?
Yeah, so that's a great question. So here, epsilon is like a local error bound, right? It says this specific approximation, you incur this much error. You're right that this isn't tracked at the type level. So like if we then do some additional range reduction on top of it, maybe that error grows, or maybe it shrinks. I don't know. I've done related work on tracking how these errors kind of propagate through the program, and I think also it's a little related to this question about verification. Right now, these error bounds don't contribute in any way to like the compiled output or to the type checking besides this local one. But yeah, I think that would be interesting. I've been hoping to integrate some of this approx functionality into my tool Herbie, which is kind of like where my research typically ends up being deployed, and there we'd have to track it.
Thank you.
If you're a student who wants to do some of the work that people are asking me questions about, like I'm in the market, talk to me.
I'm not actually a student, but I am interested in doing some of the work. But first, I'm going to make your life a little bit more difficult. There are a few numbers that are extremely difficult to compute, say, the sine of.
That's right.
And certain implementations will literally just handle these by case.
That's right.
And sort of start, OK, if it's this thing, here's the answer, don't ask why. Can you do that? How does that fit in? Because doesn't that sort of pluck holes in your type system?
It's a great question. So, there's parts of the DSL I didn't show here. One of them is a construct called split, which literally lets you just add an if statement and handle multiple cases. It's still safe in the sense that all of the cases have to have the same type. But that type could be we implement cosine of x on the range from this number x to itself, literally a point interval, and then of course we can verify that by just checking that you wrote down the correct output. I will say, you can immediately notice floating point expertise because Martin started with there are a couple of numbers. Yeah. Any other questions? Probably time for one more.
Yeah, super interesting work. Is it possible in your little DSL and type system to implement arbitrary computable functions with loops and things like that?
No.
Other than polynomial, if you want maybe to compute Newton's method or I don't know.
Yeah, that's a great question. No, there's no option for loops. There's some limited support for conditionals. I'm not sure this is like a deep, moral statement, but it's much easier to verify loopless programs. Obviously, the concerns about like type systems, et cetera, are simpler. And to be honest, typically these mathematical functions don't do that, right? Even, you mentioned Newton's method, for example. That's pretty common for use inside implementations, but typically you have some fixed number of iterations because each iteration like improves your error bound and you know the maximum number of these. That also, by the way, makes it much easier to determine like how fast a program is because typically you only have a couple of program paths. So it's, you know, you can approximate that by like, the program is just this fast for all inputs.
Thanks.
All right. So I think that's it for me. And let's switch to our next speaker.